let's start the session. So I welcome you all to the week 3 interactive session. Today we will be discussing the previous year's assignment questions on the week 3 topic. Before I get into the questions, do you have any doubts specifically from the from professor's lecture? Any specific topic that you are not clear with? You can unmute yourself and speak, or else you can write in the chat. So we can directly go to the questions. Normally, or I'll take you through the recap of what were the topics discussed. Yeah, so the week 3 lecture, I think, started with the kernel structure that is with the layered approach. Now, how different operating systems are designed and the pros and cons of each of those approaches. So, one of the topic that was discussed was on the layered approach. It's like, since operating system is a very complex code, one can develop the whole functionality in a layered manner. Okay, I'll learn better. I'll share my screen. It's visible. Is the screen visible?
Yes, ma'am.
Yeah, thank you. In the layered approach, one approach is to design the operating system as multiple layers, wherein the layer 0 will be the hardware layer, layer 1 will be the layer that would be interacting with the hardware, layer 2, layer 3, etc. will be the outer layers, and layer n will be the layer that interacts with the user. In such an approach, the major advantage is that it is very simple in case of development as well as debugging. Because if an issue, if we observe any issue, you can start from layer 0. Layer 0 being the hardware, we assume that there are no issues there. Then we check out that layer. If that is not there, okay, then the issue will be anywhere from layer 2 to layer n. Then you move to the next layer. So suppose when you are at layer 3, and if you find that, okay, that layer is having an issue, we were able to identify clearly the issue is in that particular layer. So that is one major advantage of this particular approach, that is the layered approach. The disadvantage of such an approach is that, first thing is, the operating system provides a lot of functionalities, right? So we need to identify this layered mode of implementing these functions. So which functionality will come in which layer, which will come in the inner layer, which will go in the outer layer. So those decisions are not easy to make. And plus, there is always this communication across these layers also. In that way, this adds slightly additional overhead as well with the layered approach. And another thing is, every layer can only communicate between its immediate lower layer. So from layer 5, if you want to have use any functionality offered by layer 1 or layer 2, it will not be possible. So that is another uh, issue with this layered approach. Another approach is the microkernel system architecture. Actually, these are kind of little theory, okay. So in microkernel architecture, what they do is they try to make the kernel as small as possible by moving a lot of functionality into the user space. So the kernel will have only four few functionalities will be in the kernel, and rest is kept in the user space. So the advantage here is that it is easier to extend it, because only as if you want to add a new functionality to the kernel, one can easily add it in the user space. That is one advantage. Another, it's more easily, one can be ported it to different architecture, as the kernel is very smaller. It is more reliable because of the fact that since a majority of the functionality is being run in the user space, even if there is any error or issue in those code, it will not affect your kernel. It would still be running. It will not be crashing the kernel. But the disadvantage is the performance overhead here, because since we are moving many of it to the kernel space, sorry, the user space, there is a overhead when the communication happens between the kernel space to user space. So this is how typically a microkernel system architecture looks like. So couple of the functionalities are in the kernel, and couple of things like file system, device drivers are all will be executing in the user mode, and all of them communicate via message passing. So this is where the overhead comes in. Another architecture is using modules, that is as develop the kernel as a loadable kernel module. So this is one of the approach used in the Linux and Solaris operating system. So the core component will be part of the kernel, and the other functionalities of the kernel will be available as a dynamic loadable module. So development and further add-ons and all become easier in this case. In general, it is not that the one of the like the operating system that we use, like Windows or Linux or Mac OS, stick to one of this approach. Actually, it's a hybrid approach that people use to have a better performance and better debugging, extendability, and all. Because all these features are important, they use a mix of all these approaches. For example, Linux is a monolithic uh, because the advantage of monolith is that since the whole code is in a single address space, they are very efficient. But the disadvantage is that figuring out something that goes wrong, or when adding a new feature and all, is very difficult with the monolith. So a part of the kernel is still retained as a monolith, and other part of it is retained as a modular. So it gives you the advantages of both these approaches, and this is how typically it is done. This is the architecture of Mac OS. So they also have multiple layers. It also use microkernel plus modular architecture. So yeah, so this have a portion of kernel running over it. Then we have the system calls layer running on top of it, and the library interface and the applications on it. So these are like theory kind of thing. Then, in case of Android and all, how it is done. So, Android is based on a Linux kernel, and it's currently available as open source. Then, the Android architecture, you can go through these things. Yeah. Then another topic that was covered was operating system debugging. When we say operating system debugging, there are two aspects to it. One is finding out if there is any error is there, if there is any bug, then finding out that and fixing it. Another one is with respect to the performance aspect. If by some reason the operating system is not performing at the speed at which it is expected to, then that also requires some kind of debugging. We need to fine tune, one can fine tune certain parameters and then make the system perform as expected. So in case of errors in general, operating system generate log files containing the error information, and in case if a crash happens, system failure or a crash happens, a crash dump is also generated. So crash dump is nothing but a memory dump. So one can relook at the core dump or crash dump and then figure out using this debugging tools like where in the code this issue happened and what was the state of the program when this crash occurred. Those things can be retrieved from the crash dump or the code dump. Then to do a performance tuning, there are some tools and all available, like profiling, tracing tools are available, which help us look at the CPU consumption, memory consumption, and other aspects, and then figure out how the system is performing, and then accordingly we can do the fine tuning. So, for example, in Windows, if we go to a task manager, we can see which process is consuming what amount of CPU memory and all. On a similar line in Linux, we have the stop command. For example, if you see this, this is the output of the top command. So it will tell you like what process is running, how much is the CPU percentage used by each of the process and all that. So currently, if you see this particular machine that I'm looking at, the CPU and machine is pretty stable. If you see, there is nothing actually running over here. Memory and CPU utilizations are very, very low. But the moment I spin up a simple process, with some while loop or infinite loop, we can see that it would just shoot up. Maybe we can just take an example. For example, if we simply write a C program to have a while loop. So I had just added a while loop. And now if you see how much is the memory consumption, can you see here? So this command gives us, so the add out that I just executed, it's occupying the CPU completely. So stop command can be used to figure out why I kill the process or the program. See, it's back. So these are the there are many more tools. This is one of the very, very simple tool available. Okay. This is about operating systems are in general designed to. One second. Yeah, so operating systems are generally designed to run on it's normally designed to run on a generic way, right? To run on a class of machines, and that system must be configured for a specific use case and all that. So this operating system generation or NSysGen, it's a program that obtains the information concerning the specific configuration of the hardware. Then this can be used to build an system specific compiled kernel, and then one can have more efficient code than the general kernel. So uh, one give me a minute. Sorry. Yeah, so when you build a system with specific hardware, or when you have some insights into the underlying hardware system, and when you're building a code or a program with respect to that, we can actually do a lot of optimization that help us have a much more efficient code than a generic system. So this end system is used to achieve that efficient code from a generic return operating system kernel program. So then, the other aspect that was discussed is about the system boot. So in general, I think it was already discussed in the earlier class that when the operating system, when the machine first boots up, the what you say, the bootloader is loaded from the ROM, right? So sometimes it's like that. If there is only, for example, if you have a dual boot system and all that, then how do you choose between which operating system if you want to load for example, you have a laptop that have both Linux or Ubuntu and Windows on it. So when the system boots up, we get a menu, right, to do up and down, and then we can choose which operating system currently you want to load into the system, and then boot up. So that is normally provided by a bootstrap loader called grub, which allows the selection of kernel from multiple available kernels in the actually in the hard drive. Okay. Then based on the one that we choose, the that operating system gets loaded into the memory, and then the system will boot up with the Windows or the Linux OS that we have chosen. So that is also another way of having loading the operating system into the memory. Yeah, then after that, the concepts of process starts in. So I think in the earlier session as well, it was slightly touched upon the concept of operating system what to say, the thread, etc., was also slightly touched upon. But further on in the upcoming week and all, the concept of process, threads, process scheduling, process communication, all these aspects will be covered in depth. So, as we have seen, a process is a program in execution. So, first, all the process execution, it actually proceed in a sequential manner. So, we also know that process is an active entity, whereas program is a passive entity. It's a instruction written which is residing in the memory, but process is when these instructions are getting executed by the CPU. So we can start the execution of the program either using GUI or using the command line. So as we saw here, the this what I have done here is this is actually starting. I'm running this program. Okay, so this is via CLI. I am actually starting a process, right? So this is one way. In Windows, I think we normally use the uh, we can use GUI. We can use GUI also, but yeah, in this machine that I'm showing here, we are starting the process using a um, command line. Okay, so one can start either using a GUI or a command line. So as I started this, you can see that a new process got created. See, you can see this is a new process if you see this PID. So a new process was created. Okay. Yeah, so we can have multiple users executing the same program at the same time also. So it's also possible. For example, there is some editor on a server machine or so we have some editor software available which multiple users log in and consume that same the process or use that software for various purposes. So multiple users will be executing the same program, but to cater to each user, a new instance of the program will be spinned up so there will be having multiple instances of the same process running catered to these n different available users. So this in the structure of a process is more than the program code. So a process majorly, okay, I think, yeah, this is how typically this is the process structure of a process in memory. So this text portion comprise the code in or the instructions. The data will contain the variables, majorly the static and global variables will be present in the data structure. Then the all the local variables, function calls, all that would be in the stack section, and the dynamically allocated variables will be there in the heap section. So if you see a process majorly comprise of a text or a code section, data section, a stack, and a heap. Okay. So this is how the memory limit for the process will be from 0 to this number. So this will be the limit, memory accessible limit for this particular process. So in general, the stack is allotted from the limit to the bottom and heap grows from bottom to top. Stack grows from top to bottom and heap grows from bottom. So this area will be used during the running of the program. Whenever there is any new variables created, when a new function is executed, the parameters, all that goes into the stack section. And whenever, are you all aware of dynamic memory allocation and all? Sometimes in programs, we will have to dynamically allocate memory. That time, the allocation actually comes from the heap part. Okay. Then is the process state. So there are majorly five state. One is as it starts executing, its states keep changing. One is new, that is the process is being created. Once the process is moved from the secondary memory to the primary memory, it moves to the ready state. So new when the process is being created, and when it is admitted to the main memory, it goes to the ready state. Okay. And when from the ready state, it means that it is waiting for the CPU for start the execution. So from the ready state, it moves to running state once it is provided the CPU or it is scheduled. Okay. The process of allocating CPU is also called as scheduling. So when the process gets scheduled, when the process is allocated CPU for execution, it moves to the running state. Okay. Now in the running state, either it can run to completion and then exit, then it goes to the terminated state. Otherwise, sometimes the process will have some input output operation. For example, if we are taking some, if you are reading some input from the keyboard, for example, you have written a code that adds to number and you are reading the numbers from the keyboard. So you will be waiting for the input to be given, right? So it's an high input operation. So that time, when the process is waiting for an IO, it will be moved out. The CPU will be taken away. It will go to a waiting state as it is waiting for the IO to complete. And once the IO event is completed, like when the user gives the numbers like 1 or 2 or 10 or 15 is entered, it then again goes back to the ready state. Once the IO or the event is complete, it goes back to the ready state so that again it can start execution when the CPU gets allotted. In addition to IO, sometimes some interrupts can happen in the middle. In that scenario, as the CPU needs to as the interrupt service routine needs to be hand taken care of, interrupts need to be taken care of, the currently running process will be moved to the ready state. Then the kernel will take care of the interrupt, and then again after that the process will be scheduled back. So these are the different states of a process. So in general, the process, particular process goes through these states when it is starting to ending execution time. Okay. Any doubts here in the process states? Any doubts? You can unmute yourself and ask in case if you have any doubt. Okay. So the other next one is process control block. Every process, like the process state, at a given point of time, a process will be in a particular state. Okay. In addition to that, a process will have a lot of information pertaining to it. All this information is stored in what is known as a process control block, or also called as a task control block. Okay. So the couple of there will be lot of information stored in this, but few of the information is like the process state will be captured, in which state, as we saw there are multiple states the processes. So at any given point of time, a PCB will have what is the current state of the process. It will have the process number or PID. It will have the program counter value, that is the next instruction to be executed for this particular process. Then it will have all the register information, what are the various CPU registers allotted used by this process, and what are the content of all these registers that will be tracked here. In addition to that, the memory limit, the allowed range of memory that the process can access. And then it will also have the what are all the set of files that this process have opened during the course of execution. Then there will be a memory management related information, the memory allotted and all that, especially the page table and other informations are there. So we will all this will be dealt in the upcoming week. What memory management information will go in this PCB. Then certain accounting information like which CPU is being used, time elapsed since start time, how long it have been allotted and all that. In addition, there will be IO status informations also. What are the input output devices currently allotted to this process? So PCB comprises all the information associated with a particular process. Okay. And thread is, as we have seen, thread is nothing but uh, an instance of a process, we can say. So far we have, whenever we have told process, it means a single thread execution. Uh, there is a possibility that multiple threads will be running. So in such cases, a process can have multiple parallel threads in execution. In that case, every thread might be executing at a different point in the program. So there will be multiple program counters available. So how the PCB looks like for a multi-threaded scenario will be covered in the upcoming lectures. We will take a look at it that time. Okay. So this is a simple representation of this task structure in C. So PCB is called as task underscore struct in a Linux kernel. So there, it's a very large structure actually. It contains a lot of fields, of which few are listed here. First one is the PID, process ID. So as we have seen, so this is the process ID. Whenever we term, yeah, this is the process ID. PID you can see here, right? So that is the process ID. Then the state of the process, running or waiting, ready, all that. Then the other thing is this is time slice is the scheduling information, how long this process have been given the CPU for execution. So we'll see this concept of time slice will be more clear as sir will explain the scheduling algorithms in the upcoming lectures. Okay. The other parameter is parent and children. So in Linux, there is this notion of parent-child relationship between two process. So the process that creates the child, so it becomes the parent and the other becomes the child. For example, if there is a process P1 and it creates another uh, process P2. So this P1 becomes the parent and this becomes the child. So in Linux, there is this hierarchy of parent-child relationship between different processes. So we'll see that with an example. Okay, I have, yeah, so let's yeah, we'll see that with an example. Then the list of files that are open, then these are the address space accessible. So all this information are available in what is known as a task structure in Linux kernel. Okay. It's only a snippet of it. That structure is a very large structure. Then the other concept that we have to learn in the process is like process scheduling. Okay. So as we know, there will be multiple processes running in a system. Every process needs to get some share of the CPU for its execution. So this is taken care by the operating system using that in scheduling policy or operating system have what is known as process scheduler, which takes care of picking some process from the ready queue and allocating CPU for that. Okay. So, so the agenda is to have a process scheduling is to maximize the CPU use. So, if only if there is no CPU scheduling, there is only sequential execution, then every process will be executed only after completion of the earlier one. For example, if we had process P1, P2, and P3. Okay, if there was no CPU scheduler, process P1 will execute, and in case if it is having some input output operation, it will the CPU will wait during the input output operation. And then once the IO is done, again P1 will continue. Then once P1 is completed, it will start executing P2. Again, then when P2 is having some IO, again CPU will wait. Then once again P2 will continue once the IO is done, and then P3 will be started. So there is a lot of time the CPU gets wasted, right? CPU time is getting wasted if we don't do the parallelizing. So with to improve the CPU utilization, we what we do is when P1 is going for IO operation, P1 is going for IO operation. What we do is we schedule P2 so that CPU is not waiting idle. Then when P2 is going for IO, what we do is we go to P3. So, so that at any given point of time, CPU is not wasted, and thus we maximize the CPU utilization. So, operating system takes care of this process scheduling. So, there is a uh, scheduler running in the kernel that takes care of selecting among the available processes in the ready queue for the next step execution on the CPU. So when it comes to scheduling, so these processes that are ready to execute, that are available in the system, will be waiting in some queues, and the scheduler will take this process from one of these queues, and it will schedule the process. So we have something called a job queue. IS maintains couple of scheduling queues. So we have something called a job queue, a ready queue, and device queue. So job queues are set of all processes that are in the system. Okay. So some of that process might be, it would still be in the secondary memory. Some would be in the main memory. So a ready queue comprises a set of all processes that are residing in the main memory. So job queue will contain a set of all processes in the system. Ready queue will contain set of all processes residing in the main memory. So this will be the in the new state. This is in the ready state. Then device queues contain set of processes waiting for the IO for that particular resource. So and during the course of scheduling and process execution, different processes migrate among these various queues. So, for example, if you see here, ready queue and various IO queues. So, in the ready queue, currently we have process 7 and process 2. So, PCB is what we keep in the queue because from PCB we get all the information necessary to start that process execution. So we have a process 7 waiting in the ready queue, and we have process 2 waiting in the ready queue. So we have two processes in the ready queue. And these are other queues which are currently this is our device queue corresponding to magnetic tape. Currently, none of the process is waiting to use this device. Again, magnetic tape unit 1, no process is waiting to use this device. Now, disk secondary storage, disk unit 0, we can see that there are three processes in the queue. So process 3, process 40, and process 6. All these three of them are waiting to use the particular device. Now, this is a terminal, like your console terminal, output terminal, monitor, or anything. We can see that one of the process is waiting to use that particular device. So, like this, there is will. So these are device queues. So every device will have a queue which will contain the list of processes that are waiting to use that particular device. Okay. So, ready queue will contain the set of all processes that are ready and ready to start execution. They are just waiting for CPU. That is, they are just waiting to get scheduled. Next is representation of process queuing. So, for example, if we take the process scheduling, like from the ready queue, it is allotted the CPU. So once the process is done with execution, it will go to the terminate stage. Okay. Otherwise, if it doesn't complete execution, instead it is having an IO request. It is trying to read some value from the keyboard. Okay. So then this process will get added to the queue of keyboard device. Okay, it will get added to the queue of the keyboard device. Then once the entry input operation is done, it will go back to the ready queue. This is one scenario. Another scenario is this the CPU time allotted for this process expire, that is time slice expire. So in general, in scheduling, we will the operating system or the scheduler allots some time slice for execution, like some micro or milliseconds for each process. Okay. So if this process execution time is over, suppose 10 milliseconds was allotted for this process, and if the time slice is expired, then again it will go to the ready queue and it will wait for it to get scheduled again. Hmm? Now, if the in the program now, if we are forking a new child, okay, we are creating a new child from this process, then that child will execute and it will go to the ready queue. In case if there is an interrupt, then the interrupt will the interrupt gets serviced, and then again once that is done, it will again go and wait in the ready queue. This is typically how the flow of the process in general during process scheduling. And this is the CPU switching from one process to another. For example, so process 0 is executing here. Then in between, an interrupt came for a system call. So what happens is we will save the state of the process into PCB 0. Then the system call interrupt will be handled. Then once the interrupt is done, we are reloading the state. We want to execute another process P1. So we load the state of PCB1 now. Then we are so here we are saving the state of PCB0. Now if after the interrupt, if PCB1 is getting executed, process 1 is getting executed, the process control block of that process is loaded, and then again that starts executing. Okay. Now again, if the time slice expire, then again PCB1's state will be saved, and PCB zeros state will be reloaded, and then it goes for execution. So this is how in general the scheduling or switching between processes happen. So there will be a save and a reload when it is switching from one process to another. Okay. Then, so when there are mainly, as I told, schedulers are actually responsible for allotting CPU to a particular process. So they choose one process from the ready queue and then allot the CPU to that particular process. So there are mainly two types of schedulers. One is known as short-term scheduler and the other is long-term scheduler. So short-term scheduler or CPU scheduler in general selects the process from the ready queue. Okay. So in the ready queue, we have all the processes that are ready to be executed, right? So this short-term scheduler is also called as CPU scheduler. So it will select one of the process from the ready queue and allot CPU to that process. Okay. So the frequency of short-term scheduler invocation is very high because it's in the range of milliseconds. Due to that very reason, since this scheduler keeps getting invoked every millisecond, the scheduler logic or the functionality implemented in the inside the scheduler logic also have to be very quick. So the scheduler have to make the decision very fast. So given a set of n process in the ready queue, which process to choose from the Zen, this decision must happen very fast. Uh, the other scheduler is the long-term scheduler. So long-term scheduler decides which process in the system must be admitted and go to the ready queue. So it decides which all process should be moved from copied from the secondary memory to the main memory and go to the ready queue so that process will further get CPU and it will run to completion. So these long-term scheduler or job scheduler, they are not as frequently invoked as our CPU scheduler. So their frequency of invocation is in general in seconds or minute. So one can have the logic. Long-term scheduler logic also can be little complex enough such that one can control the degree of multiprogramming. So when we say degree of multiprogramming, in general, in the system, actually we need to have a good mix of IO bound and CPU bound process. For example, an IO bound process is a process that spend a lot of time doing input output than doing computation. There will be a lot of read write from the input and output. Whereas CPU-bound processes are more compute-bound process. They will have minimum I/O operations in it. So, if we have all the process as compute-bound, so CPU will be full time busy executing, and the I/O devices will be busy, all will be free, idle kind of. Instead, if we have all the in the ready queue, if we have a lot of IO bound process. So all these processes will be going for IO operation. So they'll be waiting in that device queues and CPU will be staying idle. So to avoid this, if you have a mix of IO and CPU bound process, when the IO bound process goes for IO operation, the one can schedule the CPU bound process so that the CPU will be consumed. And same way, instead of having completely CPU bound process, if you have some IO bound process, these IO bound process will you consume the IO devices as well. So it's always good to have a good mix of these IO and CPU bound process and long term scheduler, and that mix is actually called as degree of multiprogramming because how occupied or how well the IO and the CPU is utilized decides the degree of multiprogramming. So, long-term scheduler can have some complex logic running so that it can choose the processes or it can admit the process such that this there will be a good mix of IO and CPU bound process in the ready queue. Uh, yeah. Now, yeah, this was with respect to the normal operating system. With respect to the multitasking in mobile systems, in general, like in Apple and all, they it doesn't allow multi tasking. Actually, it allows only one process to run at a time. So, but in the starting from iOS 4, it have started. Providing two process to run. One will be what is called as a foreground process that the GUI and what we normally the user will be using. And then it also allows multiple background processes running in the memory. So this is limited. They have limited, though the underlying kernel will support. They have limited it because to reduce the power consumption and to increase the efficiency because on mobile devices power is a for very concerned, right? So to for that they normally keep this restriction is kept. Okay. In Android, runs foreground and background with comparatively lesser limits. iOS have more limits on the number of background processes than Android. So in Android, this background process are they use something called as servers to perform certain tasks actually. So this will not have any UI and their memory footprint and all will be very minimal. So that is how see if you see you see the difference here like in a desktop or on a server the operating system have a different set of requirements, right? So its capabilities are also different, whereas in a mobile device given the constraint it have the operating system scheduler is also designed accordingly, and the multitasking that it allows is also minimal. Now, context switch is like as we have seen in the previous slide, right? 1 second. So here we are running one process P naught, then we move to P1, and then we again come back to P naught, right? So this is called as a context switch. So you're switching from one process context to another process context. And this involves saving the PCB of the old process, reloading the PCB of the new process, then start execution of the new process. Now, when we are switching back from the context of this process P1 to the context of process P0, again we are saving the state of process P1 and reloading the state of process P0. So this is called as context switch. Yeah. So this is actually a pure overhead for the system. The CPU or the system doesn't do any useful work during that point of time. So uh, the longer the context switch, less would be the performance of the system. So uh, in general, context switching is considered as an overhead, and the operating system designers always try to keep that minimum using sometimes using some hardware supports, etc. Also. Now, on the operations on process, any doubts till now? In operations on process, majorly we have uh, process creation, termination. So let's first start with a process creation. A process can create another process, and in Linux it's normally created using a fork system call. Okay, so process create children process, which in turn can create other children process, and each process is uniquely identified by a PID. Okay, and the in Unix the init process PID is one. We can see it here. If we ps minus AX. If you see here, see, you can see in Unix it is init is called system D. Okay, system daemon. So you can see the process ID. So this is the first process that was created. The first process in the system. Okay. And every process will have this parent child relationship, and one can actually build this tree looking at the process ID and the parent process ID. This is the scenario in case of Unix like operating system. Okay, so when a process creates another process, there are two things. One is resource sharing among parents and children, and the other is execution option. So sometimes parent and children can share all the resources. In certain cases, children share a subset of parents' resources, and in another case, parent and child share no resource at all. So all these three possibilities are there. And in case of execution options, there is always possibility that the parent and child execute concurrently, or parent waits until the child terminates. So these are the uh, options available. So whenever a parent creates a child, either parent and children can execute concurrently, or the parent can wait until the child or the children terminates. In case of resource sharing also, either they can share all the resources, or the parent and the child can share a subset, or no resources at all. So these are the various options. In if the same thing with address space. So a child is a duplicate of the parent address space, and a child loads a program into the address space. So in case of address space, child is actually have the duplicate of the parent address space. And if the child is going to execute a completely new program, then it loads the in the duplicated address space, it will load its new address thing. Okay, it will load the new program into that address space. So let's take a look at the Unix call fork and exec. Fork system call creates a new process, and exec system call is used after a fork to replace the process memory space with a new program. Okay, so let's take a look at a fork program. Okay, so I have a program here. So it just do a fork, okay, and it will print hello world. That's it. Hmm? So let's comment out this portion of code. As of now, we will comment these out. Then when we see the PID part, we can come to it. So this is the so I have written. So this program is written in C. This I'm compiling it. Now I am running it. So can you see here? We have it have printed hello world twice. So what was the in the program? What I did is I have created a from this parent process, I have created another process. Okay. And as we told, the parent and the child will have the same, they share the, initially they will share the same address space. So both the parent and the child will execute this line, this instruction. So that is why we have got, when I executed the program, we got hello world printed twice. Once printed from the parent process and once another printed from the child process. That is, um, so I had a P1 and then I'm creating P2. So after P2 also have this print, P1 also will execute the print statement. So that's why we got the hello world twice. Because they copy the initially the parent and the child share the same address space. So that's why we got both the prints here. Hello world came twice, right? Now we'll see the PID thing. Okay, so I'll explain. Then in when a process creates, so what happens is, so when P1 creates P2, what P1 will get is PID of P2. So P1 will get the PID of P2. What P2 will get is 0. Okay. So so I am having a for call which will return a PID. Okay. Hmm. Now after this for call, after this for statement, if I keep a check on PID 0, it implies that, and then this for call will return the PID of the child process to the parent and 0 to the child. Okay. That is the how the system call works. So it returns 0 to the child and it returns the PID of the parent, sorry, PID of the child to the parent, and to the child it returns 0. Okay. So now let's execute this program. So now what I'm doing is I'm calling a fork here and I'm copying the PID to this variable. So fork will return me the PID. Okay. Now based on whether you are the child or you are the parent, the value that you see will differ. So if you are the parent, you will see a different value. If you are the child, you will see 0. Okay, so we'll see whether we get only one print or whether we get two prints. Let us see this. Okay, so we got both the prints. So which means that from the parent, we got it went into this portion, and from the child process, we got this print. Okay, we'll show one more thing. So what I'm doing is after this creation, no, I'm doing a while one. Okay, so it will just loop both the parent and the child will execute the statement. So they will just what does while one do? It will infinite loop, right? Now let's see the parent-child relation after that. Okay, so it's going into a loop. Now let's see our PS minus L. Okay, so can you see this? There are two processes here. Yes. Hmm. And if you see 397, this is the process ID of the parent. This is the process ID of the child. And you see here, this child's parent is this. So if you see top, what are these fields? So this is process ID and this is parent's process ID. Okay. So this is the process ID of P1. So it has a different parent. We'll see who is this parent. Now this is P2, the child that we created using the for call. See what is the parent ID? The parent ID, it is this the P1. Are you able to understand? Hello? Maybe I'll share that is so we had P1 and P2 and the process ID of P1 is 3971915. 3971915. P2 is 3971916. Right. And for P1's parent is somebody else. We'll find that out. But P2's parent is, if you see here, P1's parent is this guy. We'll find who is that person. Now this is P2. P2's parent is this one. So, sorry. There is this parent-child relation, right? And this is the children, which implies that P1 is the parent of P2. Now let's find who is the parent of P1. So what is the parent ID? 3939978. 3939978. 39978 is bash. That is this terminal. So I have launched it from the terminal, right? So that is the parent, right? So this way we can build up the tree actually. So this is bash. Bash was the parent of P1. Okay. Now one more thing you can see that, see I'm having a while loop. So it's still going on, right? So now if you use the stop command, you can see there is 100% CPU utilization by these. It's looping there infinitely. So you can see that the CPU utilization is also going up. I have ended the process. Now let's see if the process is available. 2s minus. See, we don't have the process anymore. We don't have it. Okay. That is one thing. And one more program that that I have is sorry. Yeah, this is this one. So I think the example program that was there in this slide, I believe. Right. So let's see this also once. What it is doing is, so I will have a fork as we learned in the week 1 and week 2. The system calls always return us. In case if there is an error, we can figure out if the PID is less than 1, it implies that the process creation failed. Okay. So now if it is PID equal to 0, The child process will execute this portion of code, and in the child process, what we are replacing it with a new. We are using the exec system call XCLP, and we are executing this code. So what will happen is the address space that was shared will be replaced by this this code. This program will be executed in the child. Okay. Now else part is the parent. Parent is waiting. Okay. Waiting for the child to get executed, and then once the child execution ends, we should get this print. So order of the print will be first this will come, then this will come, then the ls output should come, and after this command, after the ls output, the child terminated should come. Let's see how it is coming. Can you see? So I have executed L. So this is the output of ls. Okay. So exactly the same thing we got using XLP. So we had the parent, then the child is executing. XLP is executed. After execution, the child have terminated, and all the process. Now what happens if we put a while one inside that? Let's try here. After this, if I do a while one. Let's see if this child terminated print will come. Whether it will come or not. Why is it not coming? Oh, okay. That is because this portion of code is replaced. Okay. Because that the with XLP, we replace the address space with this code, right? So now no longer the it will share the address space. So that's why it was not having any effect. Okay. Okay, now I think I'm done with the lectures. Probably we can go back to the previous year questions now. Yeah. Yeah, so the first question, what else is referred to as a process control block? Control block, task control block, memory block, or data block? Can you please unmute and speak? It have been a one-way conversation all this last 1 hour plus. Or at least type something in the chat, your answers. Hello? Can one of you type the answer in the chat? What is the other name used for process control block? What is the answer? The answer is correct. It is also called as, the answer is B. It's also called as task control block. See, the next question is, which of the following does a microkernel facilitate? Reliability, extensibility, portability, all of the above. What is the answer here? Which of the following does a microkernel facilitate? Reliability, extensibility, portability, and all of the above. Any idea? So the answer is all of the above. So a microkernel actually improves, make the extensions easy because they keep the kernel very small. Or major, but only the core functionalities are kept inside the kernel. Rest are moved to the user space. So adding a new thing to the kernel is equivalent of adding something to the user space. Same way with portability, as only a small, the kernel is small. It's easy to port it across onto different hardware platforms. Same, the reliability is majority of the things run in the user space. Even if something goes wrong, any extended functionality goes wrong, also the kernel would still stay safe. There won't be any kernel crash happening. So in that way, microkernel actually facilitate all the above. What it does, what the issue it have is with respect to performance actually. So the answer is D here. The fork system called returns. This please answer. I've explained little before. Fork system called returns. PID of parent to child and zero to parent. PID of parent to child and PID of the child to parent. PID of child to parent and zero to child, and none of the above. So can you please type the answer? Any idea? Yes, the answer is correct. It is PID. The fork system call will return PID of the child to the parent and zero to the child. So that's what we have seen in in the sample C programs also. Any doubts anybody is having? If you can't unmute and speak, you can type in also in case of any doubts. You can type in the chat whatever if you have any doubts or anything. So the next question is, which of the following is not true? Okay. Process scheduler selects among the available processes in the ready queue. Time sharing of methods minimizes the CPU usage. The process gives up the CPU when an IO request comes, and none of the above. One second, I'll be back. Yeah, so the answer is correct. It is B. Time sharing methods minimizes the CPU usage. So what does time sharing methods do? So let's take one by one. Process scheduler selects among the available processes in the ready queue. So that is true, right? It takes from the ready queue and allocates CPU. Time sharing of methods actually increases the CPU, maximizes the CPU usage. So this is the wrong statement. Processes give up the CPU when IO request comes. So that is true. It will give up when IO comes, when interrupt come, and other things. So this is true. So the answer here is B. Then the other next question is. Q5, a list referred to as dash is used to keep track of processes that are waiting to start and are located in the main memory. So what is the answer? A list referred to as dash is used to keep track of the processes that are waiting to start and are located in the memory. Okay. So what is that queue called? Uh, the queue that holds all the processes that are ready to start located in the memory. Is it job queue, execution queue, ready queue, or process queue? Answer? What is the answer here? So, yeah, so all the processes that are ready to start execution, which are residing in the memory, is in the ready queue. So the answer is C here. So the next question, what is a short-term scheduler? So the options are it selects which process has to be brought into the ready queue. It selects which process has to be executed next and allocates CPU. It selects which process to remove from memory by swapping, and none of the above. So what is once again, what is a short-term scheduler? So it selects which process has to be brought into ready queue. It selects which process has to be executed next and allocate CPU. It selects which process to remove from memory by swapping, and none of the above. So what's a short-term scheduler or a CPU scheduler? What does it do? Okay, so let's take the one by one. It selects which process has to be brought into the ready queue. Who does this job? Is it the job of um, long-term scheduler or job scheduler or CPU scheduler? So job scheduler takes care of it, selects the process that has to be brought into the ready queue, the admission. That's taken care by the job scheduler. The next one, it selects which. So this is the second one. B is the job of the CPU or the short-term scheduler. It's not C. It is the short-term scheduler or CPU scheduler takes care of allocating CPU, right? It selects which process to be executed next and then allocate the CPU to that particular process. It is done to the processes among the processes that are present in the ready queue. It selects the process and allocate CPU. So the answer here is B. So it does short-term scheduler doesn't take care of this. Okay, it selects which process to remove from memory by swapping. No, that is not done by short-term scheduler. Short-term scheduler takes care of allocate CPU to the process that needs to be executed next. Now, eighth question, next question, sorry, seventh one. The critical difference between a short-term and long-term scheduler is option one, the length of their queue, B, the frequency of their execution, C, the type of processes they schedule. So what, and then none of the above. What is the critical difference between a short-term and long-term scheduler? Length of their queue, do they differ in the length of their queue, or do they differ the rate at which they are invoked, or the type of processes they schedule? So they differ based on the frequency of their execution. So long-term schedulers are invoked less frequently. Short-term schedulers are invoked frequently, are invoked more frequently. The type of process they schedule, it doesn't matter here. They both of them schedule IO and CPU bound processes. So that's not the difference between them. Okay, so the answer here is the frequency with which they are invoked. Answer here is B. Now, next question. In regards to schedulers, which of the following claims is false? Okay, which of the following is false? Okay, short-term scheduler is faster than long-term scheduler. Long-term scheduler creates a good process mix. Long-term scheduler is responsible for process state transition from new to ready, and short-term scheduler is responsible for process state transmission from waiting to ready. Which of these is false? Okay, let's take the options one by one. Short-term scheduler is faster than long-term scheduler. That is true, right? So, short-term scheduler is executed much frequently in the range of milliseconds, whereas long-term schedulers are involved in the range of 1 second seconds. Okay, so when a particular when the scheduler is invoked faster or frequently, the scheduler has to be even more faster, right? It has to be much faster than at least that millisecond range, right? So short-term scheduler is much faster than long-term scheduler. So that statement is true. Now, a long-term scheduler creates a good process mix. So as we have seen, these processes comprise of CPU and IO bound processes, right? In general, the various programs or process that a system comprise of CPU bound process and IO bound process. So it is the responsibility of the long-term scheduler to have some complex algorithm and then do the bring a good mix of both CPU and IO bound process. So that is what a long-term scheduler does. So this is also true. Now, long-term scheduler is responsible for process state transmission from new to ready. Yes, admission is taken care by the long-term scheduler. So bringing the process from new state to ready. Ready. This is taken care. That is admission. This is in the main memory. So this is taken care by the long-term scheduler. Now, short-term scheduler is responsible for process state transmission from waiting to ready. So there is this waiting to ready. Is short-term scheduler takes care of this waiting to ready, or it takes care of ready to running? What does it do? Short-term scheduler takes care of assigning CPU to the process. That is, it takes care of process transmission from ready to running. Okay, not from waiting to ready. Waiting to ready will happen when the IO is complete. Okay, scheduler is not involved there. So the so yeah, so the statement is false here. Okay. So the answer here is B. Next question is with dash only one process can execute at a time. Meanwhile, all other processes are waiting for us. Yeah. With dash, only one process can execute at a time. Meanwhile, all other processors are waiting for the processor. With dash, more than one process can be running simultaneously, each on a different processor. Yeah, so multi-processing is like we have multiple processors and we can parallelly run multiple programs there. Multi-programming is also similar thing. Okay. So only one process can execute at a time. So when we have multi-processing, multiple programs can execute at a time. So this option, so this is not the option. With uni-process can execute at a time. Meanwhile, all other processes waiting for the processor. That is correct. With multi-programming, if we take option two, with multi-programming, more than one process can be running simultaneously, each on different process. No, that need not be. Oh, right. This statement can be true only when we have multiple processor. That is, we have multiple processor, not processes, processor. Only then the statement can be true. Okay. So this is not the answer. Multi-programming and multi-processing. So with multi-programming, we have this context switching will happen. So it's not like only one process can execute at a time. Meanwhile, all other process waiting for the processor. Okay. So this is the correct answer. D is the correct answer. So with uni-programming, only one process can execute at a time. Meanwhile, all other processes are waiting for the processor. With multiprocessing, more than one process can be simultaneously executed. So the answer here is now next question. In Unix, each process is identified by its process ID, device queue, PCB, none of the above. So what is the answer here? So you can see here. What is it? Each process is identified by what is this? What is this?
Ma'am, please repeat the question.
In Unix, each process is identified by its A process ID, B device queue, C process control block, and D none of the above. In Unix, each process is uniquely identified by this process ID. Okay. Every process will have a uniform process ID. So A is the answer. Yeah. And the next question is, if a process fails, most operating systems write error information to a new file. Another option A, new file. Option B, another running process. Option C, log file. And option D, recently used file. So I'll repeat the question. If a process fails, most operating systems write error information to a new file, another running process, C, log file, and D, recently used file. What is the answer here? No, it is not written to recently used file. Normally, errors are written to what is known as a log file. So we log the information there. That is the why the name is also log. Okay, it doesn't write to a new file or another running process or recently used file. Errors are written to log files. Okay, so the answer here is let's see, log file. Okay. So these were the questions given last year for week 3 assignments. So when is the submission date for week 3 assignment?
August.
Tomorrow. So are you all done with
Yes,
the
ma'am.
assignment? Have
Yes,
you all
ma'am.
submitted?
Have done.
Okay.
Yes, ma'am.
Okay, 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 okay. Any other doubts or queries you have from operating system? Maybe I'll log in from
Ma'am, what
another
is the correct
machine.
answer of Ma'am, what is the correct answer of question number 10?
This one. Question number 10. In Unix, each process is identified by its process identifier.
Okay, ma'am.
Any other doubts with respect to processes? Do you want to have a look at these programs or any doubts from those the fork related programs or you can type in if you have any doubts. This concepts of process is very important in the operating system. So, if you are having any doubts, make it a point to ask us, okay? Further on, we may not revisit these sections again, right? So, this is further everything, the memory management, everything is built on top of with respect to how a process wants it. So, when a process is asking for a memory, how it is done, it's all with respect to. So the fine entity that actually executes and gives us the result is the process, right? So have these concepts very clear. In case if you have any doubt, please don't be reluctant to ask. Okay. This is the question in this week assignment. We are not supposed to help you with the current assignment questions. Uh, so probably we can take it this way. What is a ready process? Which all process will be there in the ready queue? Any process which is in the ready queue is a ready process, right? So what is it waiting for in that queue? So it's in the ready queue. It's waiting there for getting something, right? What is it? It is waiting for. Then why you should ask? I was explaining this whole process, state transition, right? You want me to explain it again? So I'll explain the state transition once again. Just try if you can understand from that. Mm, yeah. So this is the process transition. So when you have true or false, you should knock out the options available. Okay. So you can try it that way also. So for example, yeah, we have this new process when it gets created. Okay, when that process is brought from the secondary storage to the primary, or maybe I'll share from another. I'll do it handwritten. Let me stop sharing here. Yeah. So, for example, so I have this. What is this new? Okay, from new, it is going to ready. When will it go? When the job scheduler takes the process from secondary storage to main memory. This is called admission. Okay. So that is when the process goes to ready. So now it is ready. It is waiting for the CPU to be allotted. Okay. Now, when the short-term scheduler assigns it a CPU, it becomes running. So CPU assigned, or we also called it as scheduled. The process is scheduled. When the process is scheduled or CPU is assigned, it moves from ready to running state. Okay. Now, from running state, it can either terminate. Terminate, it implies execution over. Execution completed. Then it will go to terminate. state. That process is done. Okay. Now, another option is if the process is having some IO. So it goes to waiting state. If it is having some IO or if it is waiting for some events, it will go to, or in case if an interrupt happens also, I'm sorry, if in case of interrupt, it doesn't go to there. If in case of interrupt, it will go here only. So in case of IO, if it is waiting for an IO and or if it is waiting for an event to happen, it goes to the waiting state. Okay. Now from the waiting state, it goes to the ready state when the IO is completed. IO completed or event happened. Okay, it goes to the ready state. From the ready state, it also goes to running to ready also it will go in case if there is an interrupt. If an interrupt comes, then the process who is running will be moved to the ready state. Okay. Now from these information, we should be able to knock out some answer there. And then what is left out will be the correct one. Okay. Is it clear? Any doubts in this particular diagram? It will, no, I cannot because that is the last option. If I comment, then you will get the answer. So I just try to understand, okay, and then figure out the answer, okay. Any other doubts from this process section? Okay. If there are no more doubts, then maybe we can close the session, or maybe last 5 minutes I can take any questions if you have. You can type it in the chat. So this state transition is something important. So please Understand that clearly and have this in mind. Okay. Okay, so I believe there are no more doubts or queries. Okay, then yeah, well, let's close the session. Thank you all. Thank you.
Thank you, ma'am.
Thank you.